if I were to revamp my calculator here as follows, by clearing my terminal window after hitting Control-C to kill that, let me go ahead and get rid of all of this meme code here, scrolling down to the inside of main. And let's just do a couple of things like this. Int x equals, quote unquote, what's x, question mark. Then let's go ahead and do int y equals get int, quote unquote, what's y, question mark. Then let's go ahead and print out just x divided by y. So here's a %i backslash n, x divided by y. This would seem to be a calculator now for division, which I can make as before. And actually, sorry, I don't want to do missing terminating. Oh, sorry. Missing a double quote there was an unintended bug. So if I make this here calculator, do /calculator, type in 1, type in 3, I get 0, which is weird. What if I do instead maybe 2 and 3? It's 0 instead of 0.66. What if I do 3 and 3? Well, that curiously works. But if I do something like 4 and 3, which would be 1.33, that too doesn't seem to work. So there's this other issue in computing when you have finite numbers of bits known as truncation, whereby even when you're trying to do floating point math, like with a decimal point, if you are using an integer, you're going to throw away everything after the decimal point unless you're explicitly using the right data type. And we saw an allusion to this earlier. If I actually go in now and change my values from integers to floats and change the %i to a %f and remake this calculator, now I can do 1 divided by 3 and I actually get back their response. But there's another issue latent here, which happens too in the real world, whereby I'm going to tweak this %f to be a little arcane. It turns out you can tell C how many digits you want to show, how many significant digits you want, if you will, by just using a dot and then a number, like 50 arbitrarily. And contrary to what you might have learned in grade school, this calculator would seem to think that /calculator 1 divided by 3 is not 0.33333333 infinitely many times. There's all this random stuff happening at the end. Long story short, this is because computers, one, only use finitely many bits even to represent floating point numbers. And if there's an infinite number of those, you can't possibly represent every possible floating point value. So we're essentially seeing an approximation of 1/3 precisely. But this too happens quite a bit in the wild. There's really no solution to this other than by throwing more bits at the problem using a double instead of a float, or at least somehow trying to detect this and catch this. That then is what we'd call floating point imprecision. But to tie this together and sort of induce a bit of fear for the coming years, these things happen all of the time. Back when I was finishing school, there was the so-called Y2K problem, or year 2000 problem, whereby for decades computers had been using not 4 digits to represent years, but just 2, because it was convenient. It was more efficient because you use half as much memory to represent maybe the year 1999 just using 2 digits instead of 4. Of course, when the year rolled around from 1999 to 2000, if you didn't have these numbers even in memory, you might confuse 2000 with 1900, which was the presumption if you're only storing 2 digits. So we screwed that up, and thankfully the world scrambled. And if you read up on Wikipedia and news articles from the time, everyone thought the world might very well end. But it didn't. So you'd think we'd have learned our lesson. Unfortunately, another such problem is coming up in the year 2038, whereby historically, since the 70s and prior, computers have generally used 32-bit integers to keep track of time, the date and the time, by means of counting how many seconds have passed since January 1st, 1970. And all of the math is just relative to that date because that's when computers were really starting to come onto the scene, if you will. Unfortunately, there's only 4 billion values you can count to, or 2 billion if you're doing negatives, from January 1st, 1970. And so on the date, January 19th, 2038, we will overflow a 32-bit counter. And suddenly, if this problem is not fixed by you or other people before the year 2038, our computers and phones and other devices may very well think it's December 13th, 1901. So there are solutions to these problems. CS50 is all about empowering you with solutions to these problems. But if you'd like to scan this here code, this will add that date to your Google Calendar or your Outlook calendar. Keep an eye on it. That, though, is week 1 for CS50. Problem set 1 will be in your hands soon. We'll see you next time.